So recently I posted something on Reddit that a lot of people liked. It was just a combination of geometry nodes and the self-fracture plugin that lets you do a lot of cool stuff with all that jazz, and it looks like you're destroying things, and it's super epic. So I want to make a tutorial on how to actually put this off in Blender because it's super simple. It's really not that complicated. So let's jump right into Blender. The first thing we're gonna need is obviously the self-fracture add-on. Oh, and by the way, you're gonna need Blender 3.0 for the geometry nodes. 3.0 geometry nodes work different from anything before that, so keep that in mind. In order to enable the self-fracture add-on, and don't be scared that my layout looks different, it's literally the same thing for you, the things I'm doing. So let's go ahead, edit, preferences. You're gonna want to go to the add-on and just type in self-fracture. I've already done it over here in the box. Enable that and you're good to go. Self-fracture is free, it comes with Blender. The first thing we're going to want to do then is create a plane. This plane is going to be what we use to shatter. It's going to need some depth, of course, because we are shattering things with dimension. Go ahead, tab to go into edit mode. Make sure in face select mode, select your face, right click, extrude face along normals. Give it as much depth as you liked and you're basically good to go. In order for the self-fracture add-on to work, it's going to require a particle system. It uses that in order to approximate where to put chunks. Go ahead into the particle side on the right side of the menu. Click the plus to add a particle system. Make sure it's on emitter, and the number here, which is basically your density, is how many chunks you're gonna get, roughly. The next thing is in source, we're gonna want to set emit from volume. This is important. And basically you're done with the particle system. Now we actually need to self-fracture our plane here, our little floor, so to speak. Go ahead and go into the object on the left side, quick effects, self-fracture. You're gonna still have complicated settings, forget all that. All you need to make sure is that it's set to own particles, so it is using the particles of the particle system itself, and the source limit is set to 0 because that makes sure it's using all the particles and there is no limit to what it's doing. Another thing you're gonna want to do is in margin, make sure that is 0 because by default it's something like 0.001. You're gonna want to enter that, type 0 and enter, because otherwise there's gonna be a margin between your chunks and that's not what we want. That's not gonna look pretty, it's not gonna look seamless when all the chunks are together. Make sure that you also put everything into a collection. In this case I'm gonna put it in a collection that's called floor chunks. If that collection does not exist, self-fracture creates it for you. So yeah, this is pretty much all the settings you're gonna need. I also like to turn show progress real time off because I think it's a bit faster that way. I'm not actually certain about that, but yeah, go ahead and click OK. And at this point, you can see that you have all of your chunks. They're kind of overlapping. There's some Z fighting right there. They're all in a collection up here. I'm going to go ahead and hide that collection. I'm going to go ahead and delete the original floor. We don't really need that anymore. And immediately I'm going to hide the collection by disabling it from the view layer using this checkbox. So in order for us to actually go into geometry nodes, we're going to need a separate object. This is going to be the object that holds the geometry nodes modifier, and it's also going to be the object that deforms the chunks and spawns the chunks. In order to see what that means, we're going to need to go into modifiers. Inside the add modifiers, we're going to press G to quickly add a geometry nodes, and I'm probably going to scale this down. It's a bit too big right now. Move it up a little bit and then apply the scale with Control A and then clicking scale, just so everything is nice and uniform in the object properties. At this point we need to bring out the geometry nodes panel. I'm just going to pull a little window out from under here. On the left side, select geometry nodes, and here we go. We're already in business. The first thing we need to do is we need to plug in our collection that contains all of the chunks. Go ahead and press Shift A to add a new node. Type S for search, and I'm just going to type in collection, and then we're going to see collection info pops up, and you're going to see that the collection info node has a input socket. We're going to want to be able to quickly input a collection into here. So inside our group input, if we go into the group node, we're going to see inputs. We're going to add a new input, and this is just going to be called geometry, or maybe just chunks. There we go. And this is going to be a collection. All right. And I'm going to duplicate the input node with Shift D and connect these chunks into the collection. So now we have access to our chunk collection as soon as I select it from the modifiers tab. There it is, floor chunks. That's it. Now immediately we can preview this. If you just take the output and put it into geometry, we are going to see that our collection spawns at our object origin. That's not really what we want. It's because we have collection info set to original. We want it set to relative, which means it maintains that offset no matter where our object is. So that's all great and good. But how are we actually going to move the chunks the way we want? Well, for that, I'm going to need to pull out my paint. That's right. So, if this is our target object, the target object is going to be the geometry of our object and what we're going to use to control the chunks with. And this is some random chunk. What we want to know is the distance between them and also a position on the closest distance. For example, if the closest distance between these two chunks is a straight line from here to this blue point right here, there's a node that can help us with that. It's just called geometry proximity. There we go, and we can see the geometry proximity node has a position and a distance. This position is that blue part, that blue dot, where the closest position on the target object is. And if we know the closest position to the target object and the position of each chunk, which we do know, as soon as we set the collection info to separate children, this basically means keep every child in mind separate, right? And then if we know these 2 points, well, and we know the object origins, their position is basically a vector from the object origin, right? There's these 2 vectors, right? So when you remove one vector from the other, you actually get another vector that is between these 2 vectors. Well, sort of. Technically the origin of this vector is still at the object origin, but I'm drawing it here to show us what's actually happening. And then we can use that vector as the direction for the push force on each chunk. Alright, so let's see what that looks like. Another thing to note about the geometry proximity node is the source position is actually something that gets figured out by the context, which means that the node network somewhere along the line is going to detect what it needs, and based on context is going to plug in the position of those points. What that means is that by default there's actually a position node here connected, but you can't see it. It's the same as if it is there, but that position node works off of context. In this case that's going to work. I'm going to show that in the end where it actually figures out what to put there, but yeah, for now just trust me that we're going to leave this socket empty, and the target geometry, which is our cube, you can see it right here, we're going to plug that into target. Faces means we need the closest point on the faces. That will give us the most accurate representation, and then all we need to do is do that subtraction of vectors that we talked about. So select a vector math node, set it to subtract. Let me just find that bad boy. There we go. Subtract, and then just set the position. This is the closest position on the target geometry, and the position of each instance. Alright, so that is simply our position node. As we talked about, it guesses that based off context, and when you plug them like that, you're going to get this new vector that we talked about, that is basically the direction of transformation. Alright, so that's pretty cool. Also, if you flip these, subtract one from the other, what this does is it flips the direction. Like, it won't be here, it will be in this direction, the vector, basically. But we definitely want it like this. Just don't worry about it. This is what we need in this case. You can flip it, but there's no point. So next up, if we simply connect that up, well, first of all, let's talk about the collection info node. What it actually outputs is an instance. So it actually outputs points which correspond to the object positions of each instance in the collection. Well, that means that in order to move these things, we need to go to translate instances. Alright, so we're going to plug in the translate instances, and over here we have the direction for translation, in which case we simply plug the vector we just got, because that's the direction we want to translate things. Instantly everything snaps to the center. Okay, the reason for that is because every object has this vector that has a distance which is based off of just the length of the vector. Basically, we want to create a map for it. Alright, the closer we are to the point, the more it pulls things towards the center. To do that, we're just going to use this distance it gives us. Now, the distance is pretty self-explanatory. It's just the distance from this position, the point on the target object, to our instance's position. So if I just draw that up real quickly, what do we actually need to achieve? If this is our cube, this is our chunk, this distance thing outputs just just the actual distance in 3D space. So if this is like 10 meters, 0 10 before all this thing outputs. But what we actually want to achieve is a value of 1 and 0 to an arbitrary distance that we're going to pick, and everything past that distance is still 0. So in order to do that, we're first going to divide this value by 10. What this gives us is a map from 0 to 1, which might seem like what it is what we need, but if we continue this map, it's a bit off center. If you continue this map, we'll see that it just keeps going towards 2, but we really want to clamp that down. So we're going to do this along with flipping it, because currently it's 0 1, we want 1 0, by just subtracting it from 1. So we go 1 minus x, where x is this thing, and we eventually get to this. Plus we have to clamp. Alright? Clamp, that's kind of ugly, don't worry about it. So if you actually clamp that, you flip it using the 1 minus x, you will get this map thing, which is what we need, and we're going to use to move everything else around. Okay, does that make sense? I hope so, because now we're going to do it with nodes. So go ahead and take your distance, and as we said, just plug it in to a math node that divides it by, technically the number here is going to be the radius, right? The radius for our effect. And then we're going to Shift D to duplicate that node, plug that into the second socket and set that to a subtract, set that value to 1, and make sure you clamp it. And at this point, what we need to do is multiply this value by our push vector, the one we got right here. We're just going to do that with simple vector math set to multiply. Go ahead and plug that in, plug this into the second socket, and nothing happens. That's because our radius is a bit slow. Whoop, there we go. You can see that we can increase that, decrease that, and it's basically working the way we want it to. Yeah, we're already halfway there. We can change this as much as we want, but what we're going to notice is that it's pretty linear. It is very linear. Like, the cutoff is way too sharp for my liking, at least. So this is what we currently have, right? We have a value of 1 to 0, that's a linear transformation, where at the edges we have 0 on the y-axis. We actually want to smooth this out, and the simplest way to do that is just to add a power. We're going to set this to a power of a, and now if I set this power to 2, you can see it tapers off, and we can control that taper off. We can control how soft the fall off is by just changing the power. Don't worry about that wiggly right line on the right side. It's technically not there in our nodes because we clamped the values. So to pull that off in here, fairly simple. Shift D, duplicate, set to power. Alright, and the exponent to 2. And if we just we need to actually change the force. That's one thing I forgot to do. We need to be able to multiply the force itself, which is done by adding another multiply node right after this one multiply, and that will allow us to change the force, not the radius. Okay, there we go. Oh, we don't want that one clamped. There we go. And now we can see that we have a much softer fall off, right? We can change the radius, and the fall off is super soft. This is exactly what we want. Yep, that is. And if we move our object, it works. We can move it now everywhere we go. It looks great. We can actually press tab and move the geometry itself. Same effect. This is what we're going for. So that helps us a lot. And these 3 nodes actually give us this map we just created. And we want to be able to control the radius from our modifier. To do that, it is very simple. Just add an input. It should be a float. And just call it radius. That is going to be the radius of the effect. Plug that into here. And make sure that the minimum value is actually 0.001, because otherwise you'll be dividing by 0, and that makes no sense. There we go. And we can see how we're now controlling it from the modifiers tab. Another thing we want to be able to control is the one second here. We want to be able to control this exponent, so we can actually go into linear mode as well, because it can make the effect look better sometimes, I've found. So it's good to just have a control for that. I'm going to go ahead and add that and just call it fall off. It controls the fall off with a minimum value of, again, we don't want this to reach 0. Go ahead and connect the fall off to our exponent. The default value for it should be 2. The default value for the radius doesn't matter that much. But yeah, now if I set fall off to 2, we'll get back to where we were. And finally, one last thing we gotta do. Actually, we're going to group these nodes now, because this gives us the map, sort of the value for clamping everything down. We're going to want to have this connected, so I selected all nodes, pressed Ctrl G to group them all together, and now they're neatly packed into here. Now you can rename the distance, radius, and fall off inside the node group itself. I'm going to do that. Distance, radius, and fall off. There we go. So now that's pretty cool. And I will name this node map, or yeah, map works because it's like a map we're using to offset everything, and now things just fit a lot better. Well, this thing is the strength multiplier that uses the map just to isolate the values. So I'm going to take my group output and add another handle for that. It's going to be called push strength. Push strength. Did I type that correctly? There we go. Push strength, and that controls the multiplier value over here, which we're multiplying the push vector by. That makes sense, right? Alright. Flip these to look better. There we go. So, that's a lot of the work done, but if you notice that if we increase the radius and the push strength, well, technically this is more of a pull strength, so I will rename it to pull strength, otherwise it works in the opposite direction. So if I make this push a little bit more, you will notice that the chunks, even though we are pushing things, they're not rotating whatsoever. The chunks are not rotating towards our object, which is something we want to do. We want them to do. That's not that complicated, because we already have a vector that points towards our geometry. Remember, if I hop into paint, we already have a vector that points towards our target geometry. We only need to use that vector to align our chunks. To do that, there's a node for that. It's called align Euler to vector, and since we're dealing with points, we want to use rotate. Now, from my testing, it's best to rotate the chunks before you translate them. You get a lot more power over the chunks that way. So rotate instances, plug that in before the translation, and then simply plug the align Euler to vector into the rotation. Set it to Z because our chunks are aligned. We want to align the Z direction of the chunks towards our object. Now, if you're using something that's not a plane and you still want things to align correctly, you might want to use surface normals for this. But that might be a separate tutorial. We're not going to be doing that right now. In this case, we're just going to use world Z up to align things. So vector, it needs a vector to align the Euler. We already have it. This is our vector right here. We plug that in, and boom, right off the bat, they're all aligned. Now, the problem is that they're all aligned. We only want them to be aligned as they go away from the center. To do that, we're going to use our map again and plug that right into factor. There we go. Now, it's a bit weak now, so we're actually going to want a multiplier for that as well, the same way we have one for the force. Go ahead and put that in here, and now we can see that as we increase, things rotate more towards the center. Now, I like to clamp this, because otherwise, if you don't clamp it, this can just keep going. But we want to only affect the edges, so press clamp, and now you see as we increase it, it just clamps towards the edge. And this is what we want. And with this thing alone, you can already create some pretty neat effects. You don't even need to have any push force. You can set the push strength to 0, and you can just change the rotation and the radius to get some really nice stuff going. Like, there we go. Check that out. That's pretty cool. So yeah, we're also gonna want to be able to control this from our modifiers. So yet another input called rotation strength. There we go. I'm just gonna split this off. My doodles are getting kind of annoying. We don't need these anymore. I'm just gonna real quickly, give me a second here. I'm cleaning these up. So now we're still, what are we doing? We were rotating. That's right, we were rotating our objects. Actually done with that. Honestly, with this we're done with basically the most fundamental parts of this, because now it works with any geometry shape. Let me give it some strength on the push in the opposite direction. There we go. It works with any geometry. You can deform your mesh as you wish. and when I exit edit mode I can't see the mesh anymore. That is a simple fix. I just need to be able to view my original mesh. Go ahead and plug in a join geometry at the end and take the group input so that we can take the geometry. Bam, now you can see both of them. Pretty simple fix. Now what else is pretty cool? So now we're pushing everything along this vector that we have created, but what if I want to rotate things around the points? You'll see what I mean in a second. First off, local space. Over here on the rotate instances, by default it uses local space, which means it rotates every instance based on its local position. So remember, each one of these chunks is an object that has an object transform, and that's what it's using whenever local space is turned on. But we can actually rotate things around the closest point on the input geometry, on the target geometry, which is this point right here. So let me show you what happens when we do that. Take position and put it on pivot point, giving it a custom pivot point, and also disabling local space. So with that done, our rotation strength will now actually control the rotation. So I can say push 0, and if we give it a little bit of rotation, you can see it's rotating around our target geometry, and this gives us a completely different effect. It's like an impact effect, like everything just goes around the geometry. It's very cool. It is very good because now it's not getting pushed away, it's rotating around, if that makes sense. If you're wondering how I'm disabling the outlines on the viewport, is this button over here. It just lets me see my effects a bit better. I have a hotkey for it. So anyway, there we go. We're also gonna want to have a switch for this, because sometimes you want to push from the geometry, other times you want to rotate around it, but we never want both really, because you see I'm pushing right now with the rotation enabled and it's just going all over the place. I mean, you can get some cool effects, you just have to play around with it, but generally we want to be able to rotate things either around local or not. To do that, it's pretty simple. We're just gonna add a boolean called local rotation. Go ahead and take some node, and this is gonna be our local rotation, which is just a float. And no, wait, it's boolean. We need a boolean because it's either on or off. And straight up plug that into here. And when we turn local rotation off, you see. We also need to be able to change this pivot because it's always on, but we want to be 0 whenever our local rotation is set to 1. So to do that, we're just going to multiply that with a vector. We're going to multiply the vector for the rotation pivot, which is just the closest point on our geometry. So if I just plug this in here, and I need to multiply that by the local value but flipped. So to do that, just math node subtract 1 minus this value, and that will flip it, and multiply. Okay, this is getting a bit like hell, so give me a hot second here. Yes sir. Now whenever this is on 1, it will actually work the way you expect it to. Things are just rotating now. Except I need to see, this is another important thing I forgot. Translate instances always needs to have local space off, because otherwise it's not working right. Or did I just lie to you? No, this definitely had to be off. But the problem is that I'm multiplying this vector by 0, 1 minus. Yeah, this is fine. It's getting pushed a little bit. That's because I have push force on. Push force need to be 0. Yeah, now you can see that we're back to this situation, and I can turn it on and off. There we go. The idea is, if you're using the rotation, you probably want push force off. I just forgot it on for a hot second there. But there you go. So now you have a control for that as well. And this is pretty good. Wow, this is getting a bit heavy here. I might collapse this. I'm not big on node management. It's really not the priority here. Don't worry about it. You can do a better job than me on this. Like, why is this way over here? Another thing that I think is pretty useful to have is to be able to rotate the affected instances. randomly, which is, I think, great if you're animating this in any way. For example, if you have local rotation, you want to be able to rotate all these instances randomly, at least a little bit. So to do that, we're actually going to have to rotate things one more time with a separate rotate instance node set after this one. In this case, we always want this one to rotate on local space. And what we want to use is a rotate Euler. Rotate Euler, plug that into the rotation, and we're going to set this to axis angle. And for the axis, which is the vector is going to be rotating around, it's just going to be a random vector. So value, random, type in random value, set this to vector, and plug this into the axis of rotation. If you want to be able to go into every direction, we want the minimum to be -1, and just forget about that. There it is. And what we're going to be changing is the angle. If I change it right now, in fact, yeah, they're all rotating randomly. And we want to isolate it so they're rotating based on our map. Where was our map? Way over here. That's fine. I will probably just take it. Now shift right click to cut it here, give it a little point so that I can reroute this so it looks nicer. You can actually tell what's happening. And one more thing, we want to be actually able to control this the scale of this rotation. So, you know, another input, this is a float called random rotation. Random rotation, there we go. And random rotation is actually right here. I'm going to use this node, and all I need to do is multiply this by the map, the random rotation by the map. And now when I bring that up, you can see they're rotating randomly. This is a bit strong though, isn't it? Rotation strength, let me lower that. Yeah, you can maybe lower the radius as well. Okay, so now you can see how points are rotating randomly the closer they are to our geometry. There we go. So that's random rotation as well. That's pretty cool. I'm glad we got that out of the way. So currently the pivot is changing with everything else. Right, the pivot is based on the geometry. When I have local rotation off, it is just based on geometry. But what if I want to keep the pivot steady at the object origin? That's a pretty cool thing to have, because check out what happens. Now the axis of rotation is not moving, so as we're moving forward, we're digging more and more into the ground. Right, it's getting pushed more inside because the rotational axis is it is just the object axis. You can even see how it's rotating around it. Okay, so in order to do that, we're just going to need another switch. So we have local rotation, which, you know, pretty obvious what it controls, but we can also have geometry rotation as another boolean. And in order to make geometry rotation work, this output right here, we just need to modify the pivot vector one more time. So another multiply node, and this is controlled absolutely by geometry rotation, just like that. So whenever geometry rotation is 0, it looks like that, and if geometry rotation is 1, it certainly uses the geometry instead of the object origin. So that's pretty much it. I hope this got pretty complicated. You could again add some randomization to the push, which would mean just adding a little node between the map and the multiply. Over here there would be a node that's just a random value, but I don't know if that's really necessary. It probably overcomplicates things at this point. So I'm pretty much going to leave it here. And thank you for watching. And by the way,